All right. Thanks for sticking around. Okay, so I'm going to talk about some recent work that I did with Ryan Rogers, who was working at Apple, on optimality, local privacy, and connecting these with communication complexity. Wrong button. Okay, there we go. So what is local privacy? Local privacy is essentially that we, providers of data, who we'll call X1 through Xn, pass their data through some kind of privatization scheme before a statistician or a learner gets to observe the data at all. All right, so in this picture, you can think of the statistician or the learner or the method as script M. It's going to spit out some estimator theta hat of some quantity or other. Before you get to observe, before the method gets to observe the data, it goes through this channel Q. Do I have a mouse? Does this work? There we go. Goes through a channel Q. It does work. Goes through a channel Q, gets privatized to become ZI. Okay, so that's kind of the game in local privacy. And then the question is, how do we develop optimal estimators under sort of constraints of this form? And I'll make this a tiny bit more rigorous. So the model of local privacy I'm going to work in, I can represent with this very clean picture. Okay? So what is this saying? So what's the game here? So the game is that we're going to allow communication and things like this of private data to happen in a fairly sophisticated fashion. So what happens is we proceed in a series of rounds, okay? And in round one, person one, that's X1, generates some data, Z1, 1, okay? And then it's person two's turn to generate some kind of data or release some sort of privatized statistic. This can depend on the previous data releases, so that is to say that Z2 can depend on Z1, and it depends, of course, on X2. We repeat this through all n participants in our study or our learning or whatever, and then we aggregate all of their data into what I'll call a blackboard. So that's the blackboard B1. So this is kind of the standard blackboard model of communication, if you're familiar with this. Okay, and then we can have another round of communication or private data release or whatever you want to call it, and in that round, call that round 2, person 1 releases Z1 superscript 2. That can depend on all the previous data releases and everything else, and we just continue this strategy on and on and on. Okay, and then this could go in rounds. You could go round 3, round 4, etc. So it's kind of the communication mechanism scheme clear-ish. One person says, yes, that's good. Vitaly is at least listening to know that I asked a question, so excellent. Okay, so then the definition of privacy that we're going to work in is, well, we'll see actually a bunch of different definitions of privacy. The starting one is local differential privacy. So we say that this whole channel or this whole communication scheme, whatever you want to call it, is epsilon locally differentially private if for any two samples, any two collections of people, X1 through N, differing in at most one entry, then the likelihood ratio of the probabilities that an entire transcript is spit out, the likelihood ratio difference between those is bounded by e to the epsilon. Okay, and so this has to be true for any two samples differing in at most one entry. So this is a stronger definition than standard differential privacy, which would allow the mechanism to see everyone's data and then privatize. But so here we have this kind of restriction that the individuals can randomize their own data. Right? Okay. And now we can relax this definition a little bit, it turns out. And so actually a quite relaxed version of this is more or less due to Vitaly and Thomas Steinke, which is that, okay, you know what? I don't actually care about having this likelihood bound all the time. Just on average, the KL divergence between what I output when I have a sample with X1 through Xn versus a sample where I've replaced the ith person, the average KL divergence between those distributions is bounded by epsilon, okay, or epsilon KL. All right. So we can, so this is essentially a much weaker version of this differential privacy constraint. Or you could also, look, it's weaker than all the sort of versions of concentrated or Renyi differential privacy or whatever your favorite DP notion is. This is more or less the weakest of them, except for a small tweak, which is that we might allow a delta probability of catastrophic failure, which leads you to epsilon delta local differential privacy. Okay, so these are the two definitions of privacy that I will work with in this talk, is that this entire transcript under this big mechanism, either on average the distributions of things that you output is close in KL or has a small likelihood ratio bound with a little delta probability of failure. Okay? So these are the definitions. Now, the only thing I want you to remember for this talk literally this is the only message, you can forget everything else, is that if you have a d-dimensional problem you want to solve, and you're under epsilon differential privacy, the effective sample size has to blow up by a factor of d, that's the dimension, divided by the minimum of epsilon and epsilon squared, where epsilon is your privacy level. That's it. So d over epsilon min epsilon squared. The end. Okay, and sort of an alternative way to think about this, or to view this, is that if you have a non-private problem that you can solve using a sample of size n, and that's kind of optimal, then if you want to solve the private version of this, then the effective sample size you need is n times d over the minimum of epsilon and epsilon squared. Or if you're doing this KL privacy thing that I talked about, you just divide d, the dimension, by this epsilon KL factor. Okay, so this is it. This is the entire message of this talk. Things blow up by d over epsilon or d over epsilon squared. Okay, so now the great thing is that I think I can actually explain this result in like 2 slides. And if I were doing this on a chalkboard, I would do the proof by hand right now, but I can do it on the slides, and hopefully we'll all be able to follow it. So there's basically 2 steps. And the first is, so first we'll reduce from differential privacy to epsilon privacy, or to a KL privacy, and then the second I'll just do a mutual information bound. So step 1, okay, this is a classic result, basically due to Dwork, Rothblum, and Vadan. If a channel is differentially private, then the KL divergence between any 2 realizations of this mechanism or channel is bounded by the minimum of epsilon and epsilon squared. All right. Basically the proof is we always know that log likelihood ratios are bounded by epsilon. Otherwise, we can just add positive numbers. That is equal to the integrated difference between the 2 channels times this log ratio. That's bounded by e to the epsilon minus 1 and epsilon. Okay. So KL divergences are bounded by epsilon squared. Now, part 2 is just, let's ask how much information actually gets released in these protocols. Okay, so if I just think, if we think of mutual information as being something fundamental, how much information are you going to get out of n people's data? Now let's ask, okay, how much information is actually carried by the observations we get, these private things z? And we can prove that if my channel is epsilon KL stable or epsilon KL private, then the average information I get per person is just epsilon. That's it, right? And the proof is like 2 lines. I mean, there's some more sophistication when you actually have to write this in the paper, but this is basically the entire result. It's the mutual information. You can write it as a sum of individual mutual informations. Each of those, because you have these KL divergence bounds, is bounded by epsilon times KL, and that's it. Okay, so the intuition is that, look, if each person's data was a d-dimensional vector, I'm getting epsilon bits out of each of them, so I should pay a penalty of about d divided by the number of bits I get to observe. The end. That's it. Okay? And making this rigorous requires some clever people doing a lot of good work. Mostly this paper by Braverman, Garg, Ma, Nguyen, and Woodruff. So we just basically can leverage a lot of their results. We should give them a lot of credit, and that's it. Okay, so let me just give a quick example. Logistic regression. So in the classical case, no privacy. If I have a maximum likelihood estimation for a logistic regression problem, then basically my maximum likelihood gets an error rate of roughly d, that's the dimension, divided by n. Okay, that's its expected loss. And with privacy, we can prove that for some numerical constant c, the expected loss you have to have is at least d over n times this privacy-dependent factor, d over epsilon, your privacy level. Okay, and I'm going to skip this little controversial position. I'm going to just say that we do have mechanisms that are optimal for all levels of privacy for a lot of statistical learning problems. Come to my poster. We can have a fun little fight if you're into privacy and what levels of privacy you should have. But I'm going to stop now since I think I'm out of time. So thanks for your attention, and I'll be in the poster room. Nati. The number of rounds does not matter. So the result, okay, so the question is, yeah, so for the achievability results, how many rounds do we need? Typically, we need 1 round to achieve them, but the lower bounds apply to arbitrary length protocols. So typically, 1 pass through the data, I mean, for like the typical learning problems we look at is sufficient. There are problems for which there are gaps, but they're artificial.
Question so
Yeah, so the question is, okay, for epsilon delta, usually we can't do mutual information. So there are two things that we do, and I kind of push these under the rug. One is that if the data is discrete, then you can do mutual information bounds, so it's fine, and epsilon delta is fine there. And two is that it turns out if you do a slightly weaker protocol where it proceeds sequentially, then you can actually do mutual information bounds by constructing close enough channels, which I would love to talk to you about. Anyway, thanks a bunch.